In the last lecture, we discussed about the basic definition of thermodynamics, and we learnt about the energy, and as I told earlier, the energy is an enticing property or entity that governs all the activities of the entire universe. And today also in the towards end, we discuss about ideal gas law, and we will have to see how this actual gas will be deviating from the ideal gas law. For that, we need to look at basically compressibility factor, or this thing which is Z. Z is basically V actual divided by V ideal, and V ideal I can write down RT by P. Keep in mind that this R is basically the specific gas constant, right. This is specific gas constant, right. And this Z, if it is Z is equal to 1, then what will happen? If Z is equal to 1, that means it is an ideal gas. If it is different than 1, it will be real gas. So, if you consider this Z, the compressible chat versus the atmospheric or the pressure in atmosphere unit at different temperatures, right, 100 degree, minus 100 degree Celsius, 25 degree and 600 degree Celsius, right. And if you look at ideal gas, this will be Z is equal to 1. So, this is corresponding to ideal gas, right. But if it is different from the 1, like it will be real gas. So, if you consider this region, which is something 200 atmospheric pressure, even like if I consider the 600, like even the ambient temperatures, right, green color, you see that there is not much change. But if I take something 100 atmospheric pressure, right, the Z is for all this temperature is very, very low, right. So, therefore, in this region, if the pressure is around 100 atmosphere pressure, right, for air, and of course, we can consider the fuel, then you can happily consider it as an ideal gas. That does not mean that there will not be an error, but that error will be very negligibly small, right. So, that you can apply. So, in all practical purposes, what we will be doing? We will be basically using the ideal gas law, but however, there are several other gas laws are being devised which can be utilized for the real gas. For example, for some of them are basically like van der Waals, Redlich-Kwong, and Beatty and Briesman, Benedict and Webb and Rubinic laws, right. But we will be using ideal gas law for our calculation, because it is quite simple and elegant to use, and it holds good for only for the low density gases, and for the combustion problem, the temperature being very high and the pressure will not be that high. If it is within 100 atmosphere, we can happily use ideal gas law for our calculation in combustion. So, question arises how to handle the gas mixture, right, because when you are saying the combustion, basically it is not the one gas, or the component of the gas will be not one, like even in air you are having nitrogen and oxygen majority, but there might be some other gases, we are not considering them for our calculations. And the product, of course, there will be several of them: carbon dioxide, carbon monoxide, water, and then unburnt hydrocarbons, SOx, NOx, several other things will be coming into picture. That means it will be basically number of gases in the combustion products, and during the combustion will be very high. Now, how we will handle those things? That is the question. For that, let us consider a container which contains like Na moles of species A and Nb moles of species B, Nc moles of species C, and let us say Ni8 mole. Then I can write down that total number of moles is basically Na plus Nb plus Nc, and it goes on till the ith species, right. And if I divide this by the N total, right, and each by N total, right, what I will get, this become corresponding to 1, right. What will be this Na by N total? What it would be? Mole fraction. That means if I look at this will be, I can write down 1 is equal to Na by N total, right. This is nothing but your Xa, right, plus like Xb plus Xc plus Xi, right. And that is basically, you can write down that basically summation of Xi. Xi is your mole fraction of ith species, Xa is your mole fraction of species A, Xb is your basically mole fraction of species B, and so on and so forth, right. But this is about mole, but if you consider the mass, right, then it is total mass will be mass of A plus mass of B plus mass of C, it goes on T ith mass. I can do in the similar fashion, that is I will divide this M total, right, and this is nothing but your mass fraction of A, and of course this will be mass fraction of B and mass fraction of C, it goes on, right. So, what it says, the summation of all the species I is equal to 1 to n, right, I can 1 to n whatever it may be, right, that is equal to 1. So, that means mass fraction of species in a container is equal to 1. Similarly, the mole fractions of all these species in a container is equal to 1. So, if I look at basically I want to now relate this mass fraction with the mole fraction. If you look at by definition, yi is equal to mi divided by m of the m mixtures, and what is mi? Mi is nothing but ni into nwi. This is basically nw is the molecular weight. And the mass of the mixture is nothing but n into mw mixtures, right. And we know this xi is equal to ni by n. In this case, n means basically n total, you can say this is n total according to the above like notation. So, this is nothing but your xi mi divided by mw mixture is nothing but your mass fraction. So, now if I sum it up, right, if I sum it up here, so what will happen when I sum it up, this one, this will be nothing but here equal to 1, yes or no. That means if I look at, that means mw mixture is nothing but sum of xi mwi. That means this is the, by this way I can find out the molecular weight of the mixture, right. If I know the molecular weight of individual species plus the mole fraction of individual species in a mixture, if I know, I can find out the molecular weight of a mixture. Is that clear? And similarly, you can find out the molecular mixtures in terms of mass fraction, that is basically 1 divided by summation of yi divided by mwi. What I suggest that please derive yourself this expression. Let us say this is your equation 1, I can say equation 2, I would suggest that you derive that expression, and which is very easily. What do you do then for doing that? Here you have sum it with the starting with the definition of mass fraction. In that case you will start with definition of mole fraction and then you will get. Are you getting? It is very easy, you can do that. Now of course also from the ideal gas law we know the N total is equal to PV by RUT. This is we know. What we will do? We will basically use this expression for the N total, right, in the I am sorry, this is basically I can say this is equation, I can say the equation A, this may be I can say equation B, right. So this is your equation 1, right, and I can substitute these values. If I substitute these values in this equation 1, right, here what I will get in this expression, if I put this thing, this will be PV by RUT, right, and equal to Na plus Nb plus Nc plus Ni, yes or no? What I will do? I will find out this P is basically, I will take all those things to here. What I will do? I will put RUT by V and I will multiply it here RUT by V. So this will cancel it out, this is nothing but your P. So when you will do that, what I will get? I will get this expression, right, I will get what? Na RUT by V is nothing but here what? This expression Na RUT by V, this expression is what? What do you call? This is a PA, and this PA I am using a small p, this is known as partial pressure of species A. This is partial pressure of species A. Similarly, this will be PB, this will be PC, this will be PI, and this is nothing but here summation of partial pressure of ith species I equal to 1 to n, it can be, right. And what do you mean by partial pressure of for a particular species? From this definition you can see that if it will occupy the entire volume, right, at the same temperature, then you call it as basically partial pressure of that species, right. And this relationship is known as Dalton's law of partial pressure, right. Sometimes people says Gibbs Dalton's law of partial pressure, right. So and Dalton's law of partial pressure is basically, if you look at the total pressure of a gaseous mixture is sum of pressure which each component would exert if it alone occupies the same volume and the temperature of the mixture, that means same temperature of the mixture, right. And of course, by this you can really connect your properties, basically the mole fractions, right, and if you know the mole fraction you can connect to the mass fractions. We have learned how we can connect the mole fraction with the mass fraction of individual species, and also the mixture we can calculate, but we need to also handle the internal energy of the mixture and also by knowing the species or vice versa, right. If I know the sum of the what you call species and mixture internal energy or the enthalpy I know, but I can find out one of them, right, that way. So according to Gibbs theorem, the internal energy of a mixture of ideal gases, right, is equal to the mole or the mass fraction of weighted sum of the internal energy of individual component of mixtures, right. And this is basically by Gibbs theorem, which is helps us to calculate. As I told that the Dalton's law is also known as Gibbs-Dalton's law. It is employed to extract properties of mixture from individual species and vice versa, right. And whereas the Gibbs theorem helps us to basically calculate the specific molar internal energy, enthalpy, entropy and others of the mixture from the constituent species, right. So, armed with these laws, we can really handle the mixtures of various components of gases. So, let us now look at enthalpy and internal energy. A question might be coming to your mind, what do you mean by internal energy? Any idea? Or enthalpy, right? How it is related? Internal energy, like it is basically microscopic form of energy due to vibration, translation, rotation of the molecules, right. That is corresponding to the internal energy, right. And of course, the specific internal energy of a mixture, if you look at U mixture is equal to sum of xi ui, where I is equal to 1 to n, right. And this is what will be unit of this ui, or what will be u? This will be joule per mole, right. And mass specific internal energy of the mixture will be yi by ui, right. And this is, that should be a bar also, okay, right. And this unit will be basically joule per kg. This will be, I can say, kilojoule per kg, okay. And this is of course without any unit, this is some number, ratio, right, the mass fractions. X is your mole fraction. This is kilojoule per kilomole unit. Similarly, specific enthalpy of a mixture can be H mix is equal to summation of xi hi, and I is equal to 1 to n, and this is again will be kilojoule per kilomole, and mass specific enthalpy of mixture will be kilojoule per kg. Now, a question might be coming to your mind, right? When I will be using internal energy, when I will be using enthalpy, what is enthalpy, right? You are having a doubt?
So, what is UI bar?
UI bar is basically, I am trying to separate the specific internal energy based on the mole to specific internal energy based on the mass, right? Because both are different, na, right? Specific means what? Per unit something. One is per unit mole, other is per unit mass. So, therefore, you will have to differentiate, na, isn't it? Okay. Otherwise, you will be mixed up, na. So, now enthalpy of species is basically, you can say H I T and 0. I is the basically ith species. I can be any species, I is just a symbol I am using. I can be nitrogen, it can be methane, it can be oxygen, and which is basically function of temperature. This enthalpy is basically function of temperature. Is having HF at the reference temperature, this is your T reference, right, 298.150, and this is known as the heat of formation, this portion, right, plus the Cpi, Cp is your specific heat into dt, right, and integrated over 298.15 to by to some temperature. It can be anything, different than the 298.15, and this is known as a reference standard temperature and standard pressure. STP, what we call, right, is basically the reference which is being taken, and this portion is your what you call sensible enthalpy, right. This is your sensible enthalpy associated with temperature. Due to temperature, it will be changeable. Keep in mind that this Cp is a function of what? Is also a function of temperature. It will be dependent on also the species. For at the same temperature, Cp of methane will be different than Cp of oxygen. Okay. And this is heat of formation due to the bond energy, right. There will be some bond, and that energy which is there with during the formation of bond, either it will be released or it will be what you call absorbed. Depending on that, we call the heat of formation, and is always being used as a standard, right, 298.15 Kelvin and atmosphere. This 0 corresponding to what? 1 atmospheric pressure, right. So, and sometimes this is also known as delta H, basically heat of formation. I have put it here HF 298, but this is a delta HF. Now, internal energy of the species also you can write down in a similar fashion, right. Right. Keep in mind that this internal energy is at a particular temperature. If it is happens to be 298, what will happen? This will be 0. This side sensible enthalpy will be 0, right. But if it is different than the reference temperature, it will be this sensible enthalpy will be certain values. Okay. Now, I had asked this question, when we will be using internal energy, when we will be using enthalpy. Is that clear? Is that question you didn't answer,
Sir, when the system is closed,
हम
internal energy का use कर सकते हैं.
हाँ, when the system is closed, you will be using internal energy, but when the system is open, you will be using enthalpy. But why it is so?
Because enthalpy is related to U plus PV, the work, the volume pressure.
But why in the open system you are using that form? Why not internal energy?
Because enthalpy is equal to U plus PV.
That is a mathematical, like some algebra, but physically. Yes, he is saying the right, the flow work which will be taking, that means flow is already taking place, right, you will have to pump. So, therefore, that is taken care, it will be easier to handle, that is all. But however, internal energy is already embedded into the system through the enthalpy. Okay. So, now we will have to basically look at enthalpy of formation, and enthalpy of formation, if you look at the amount of energy absorbed or released when a compound is formed from its stable elements during a steady flow process or at a standard state, right. Because if you look at enthalpy we are talking about, therefore, we will be talking about the flow systems. Okay. Are you getting? And standard state means 298.15 Kelvin and 1 atmosphere pressure, which is equal to 101.325 Pascal. And how, what is the meaning of that, this enthalpy of formation? If you look at, let us say there is a one O atom, there is another O atom is coming together, right, and then the O2 is formed, and then like there will be some kind of energy will be there which will be taken care, I mean like will be supplied or will be removed, like depending upon whether the heat of formation is exothermic or is endothermic. Like if it is released, it is basically exothermic, if it is absorbed, it is endothermic, right, heat being. So, that is known as the enthalpy of formations, and various enthalpy of formations right, in I have given here. If you look at oxygen of the gas is 0. How it is being done? Because the whichever is the standard state, people assume that to be 0, right. And similarly the hydrogen is 0, but whereas the water it is 242 kilojoule per mole, provided if it is gas. If it is liquid, 286 kilojoule per mole. The difference is basically heat of what? Vaporization, right. So therefore one has to very carefully use this heat of formation whenever you are handling combustion. This thing you will have to see whether it is in gaseous state or the liquid state, depending on the temperature. Okay. So of course the others are given here, these values you need not to remember, but however one has to be very careful to use it, right. And let me look at now the how this, whenever you are looking at this heat of formations for a particular temperature are little different than that of the reference temperature or away from the reference temperature, we will have to look at sensible enthalpy. When you talk about sensible enthalpy, then we will have to look at specific heat, right. When we are dealing with the internal energy, we will have to look at specific heat at constant volume, and when we are dealing with the enthalpy, we will have to work with the specific heat at constant pressure. And for an ideal gas, even for the real gas, right, there will be function of temperature, right. But in our calculation in thermodynamics, generally we do not consider to be the function of temperature for simplicity, right. But however, you cannot except certain cases. For example, if you consider, if you are using argon, helium, neon, krypton, xenon, all those gases, you need not to bother about Cp as a function of temperature, because it is remaining constant, it is a monatomic gas, right. So therefore it is really does not depend on the temperature, means the Cp values, and then both the specific heat, constant pressure and constant volume does not depend on the temperature. But however, if it is a diatomic molecules like hydrogen, oxygen, it is depend on, that means it increases with temperature, and it is what you call non-linear, it is not that linear, okay, fine. And when you go to the triatomic gases like water, carbon dioxide, it also changes, right. So now this, if I look at this, I was asking this question, internal energy basically contributed to the translational, vibrational and rotational energy of the molecules, right. And the temperature, specific heat temperature is caused by vibrational and rotational, right. And translational does not contribute to that, and of course the argon, helium, neon and other thing, there will be translation, there will be motion, but however it will not be really contributing temperature. And therefore the internal energy of monoatomic does not vary with the temperature, right, because their internal energy is contributed by translation. I have already discussed this thing, right. Now how it has to be deal with, if you look at some properties kind of things, one can use the table, right. Another way the people have used also the semi empirical formulas, right. So if you look at, they will be using Cpi, right, and is equal to A naught plus A naught A1 T plus A2 T Cp by R, right, T plus A3 T 3 Q plus goes on, like there will be several coefficient which will be, and knowing this coefficient, and this is corresponding to various species also, this coefficient will be changing with respect to species, right, and then you can get these values and then you can calculate. But however, it will be easier if you prepare a table and then you can calculate, right. So these are the temperature which is given here, and this is mean for water, right, and this is the Cp values are given here, and entropy is you can find out, it is not only the Cp, you can also use for the what you call entropy, Gibbs free energy, and this is basically delta H. Okay. This is the delta HF, which is the heat of formation which is there for these cases, and if you look at, this is nothing but a heat of formation, and this is a sensible enthalpy, right. So, similar way you can find out. I will stop over this, and we will be discussing more about the thermochemistry part in the next lecture. Thank you very much.